Hi guys, John the Quant here. This is week 5 of the Data Science Bootcamp that I am delivering to all of you guys for free and delivering for free at the Community College of Aurora. If you didn't start with week 1, I highly recommend that you start there. There's going to be a pop-up right in this area to take you back to week 1. Now, this week is all about machine learning algorithms. So what we're going to do is we're going to take a very brief, very fast look at a whole bunch of different machine learning algorithms. We're going to get an intuitive feel for the thought process behind them. And we're also going to talk about scenarios in which you might want to use those algorithms. Let's do it. We are today talking about machine learning models. And specifically, we're going to split this into two sections. We're going to talk about supervised learning, and then we'll talk about unsupervised learning. Supervised first. Now, supervised learning is when you know the answers, and you train a model to return the correct answer. Right? And that's the most common application of machine learning. Like, for example, last week, we trained a linear model to predict whether a person has diabetes. And in the mini project, you made a model to predict a student's grade on the final exam. And those are both examples of supervised learning. Now, when we predicted whether or not a person has diabetes, the answer was either yes or no. It was categorical. So that's an example of what's called classification. And when you predicted the final grade, you were predicting a specific number rather than a category, which means it was an example of regression. And we need to remember those words. Okay, classification is when you're predicting what class or category or group the observation belongs to. And regression is when you're predicting like a continuous number or an amount. Now, most machine learning algorithms can actually do both, but you will go about them slightly differently. Since we've already talked about linear models, a quick and easy kind of sidestep is support vector machines. Now, support vector machines, they basically draw a line to separate groups of data points. So let's look at this example. This is some fake data that I made so that it would look perfect like this. Now, what a support vector machine is going to do is it's going to find a line that separates our two classes, our zeros and our ones. And as you can see, there is a diagonal line that will separate them perfectly. And a support vector machine's job is to find that line. So let's go ahead and try one. So this is from scikit-learn from sklearn.svm. Import SVC, that stands for Support Vector Classifier, and we're also importing this from sklearn.inspection decision boundary display, and you'll see why in just a minute. It's a pretty cool tool. Now, I've made some fake data with 1,000 points, and every time that you're doing machine learning, you want to do a train and test split. So that's right here. The first 800 points are in the training set, and the last 200 are in the test set. And I'm fitting a support vector classifier here with a linear kernel, which means it's going to draw a straight line, which is what we want. So it's found a line that looks like 5.52 times x1 minus 7.82 times x2 minus 0.3, and that's approximately the line. But we can look down here with the decision boundary display that we imported, .from estimator, and you can see that it's found that line, more or less. And it separates our two categories perfectly. Now here I'm doing model.predict on the test set, and I've printed off a classification report, and you can see that it's fit really, really well. And of course it's fit well. It was designed, data was designed so that this support vector classifier would fit it perfectly. And it does. So that's all well and good if you're drawing straight lines. But what if we have something like this, where clearly we have these two categories, and they can be separated by a line, but that line needs to be a circle rather than straight. Well, this is called the kernel trick. It's something that exists for support vector machines, where you change the kernel. Okay, I've got a support vector classifier here where the kernel equals RBF, that stands for radial basis function. But basically, what you need to know is that this kernel lets us draw circles. Instead of straight lines, like we have up here, we can now draw circles with our support vector machine. So when we fit this support vector classifier with the radial basis function kernel, look at this, it draws a circle and it separates our two groups really well. So if we predict on the test set, and then look at that, it fits the data really well. And again, of course it does. The data was made so that this specific model would fit it perfectly. The next model we're going to talk about is decision trees. Now, decision trees are very easy to understand, and they're very flexible, and they don't care about linearity in the data. They're not affected by non-linearity, meaning that the relationships don't have to be straight lines. And you will have seen decision trees before. So this is our new fake data. I've split it into 4 quadrants. Now, it's important to think, when you're thinking about decision trees, what they do is they draw a line, and they say if you're above this line, one thing, and if you're below this line, another thing. Like this, right? If x0 is less than 0.5, then go this way. And if x0 is greater than 0.5, go this way. If x1 is less than, again, 0.5, go this way. And if it's greater than 0.5, go this way. That's how decision trees work. You will have seen these before, probably in grade school, when you probably made them by hand to help you make decisions. Well, they do exactly the same thing here. But it's important to realize that when we're talking about greater than or less than 0.5, decision trees draw lines that are parallel to the axes. So it can draw a line here, greater than or less than 0.5, and that is parallel to the y-axis. Or it can draw a line here, greater than or less than 0.5, and that's parallel to the x-axis, but decision trees always draw lines parallel to an axis. Unlike support vector machines that we saw could draw a diagonal line, decision trees only draw lines that are parallel to the axes, but they can draw as many as they need to, so they can get really, really complicated. So when I import from sklearn.tree, import to decision tree classifier, I've also imported the plot tree function. So I fit the tree here, same way as usual, model equals decision tree classifier, and then model.fit xtrain and ytrain. And then I'm looking at the model here. This is what the plot tree function does. It's very useful for that. And if I look at the decision boundary, then you can see that it's cut the data into 4 squares, exactly like we wanted it to, because this data was designed for this decision tree to cut it perfectly. Now if we look at this decision tree, as again, fit the model perfectly. And if we do it with a 3D example, you can see the data in 3 dimensions, how it's formed this supercube. And when we do the same thing, split the train and test set, fit the decision tree classifier on the training set, look at this slightly more complicated decision tree that was made, and then it fits it, again, almost perfectly. So decision trees, they have a tendency to fit the data perfectly, because it can keep making splits as many times as it needs to. Fitting perfectly might sound like what you want, but when you're making predictions on unseen data, this actually means that the model is going to do worse than expected. I mean, think about it. Like, if your model is perfect, then it can only get worse, right? And sometimes the model gets a lot worse. And now, this idea where it fits the training data really well but doesn't do so good on the test data is called overfitting. And that's when the model, it doesn't just learn the relationships in the training data, but it memorizes the training data. So it just memorizes the training data, and that's all it knows, so it's really bad at making predictions. And overfitting is a big problem, and it's what we're going to spend most of our time on next week, and we'll spend a huge amount of time on it every week for the whole rest of the boot camp. So overfitting is when the model learns too much about the training data to make good predictions, and underfitting is kind of the opposite problem. That's when the model learns too little about the training data to make good predictions. So they're both problematic, but the more common one is overfitting, because when you use decision trees, like we said, they're so flexible that they pretty much always fit everything perfectly. And there are a number of ways to combat overfitting. The 2 we're going to talk about today actually led to 2 new classes of models. The first one is called bootstrap aggregation, or bagging. And it sounds fancy, but it's really not so hard to understand. Okay, the basic idea is that we're going to take our data set and we're going to use it to make a bunch, like 100 or like 500 or like 1,000 different data sets. And we make these new data sets by randomly selecting rows of the original data set. And we don't mind if we take the same row more than once. When we randomly select rows like that with replacement, which means we can take the same row more than once, that's called bootstrapping, and it's a common statistical technique. And there's a lot of theory about how to do it well. We're just going to let scikit-learn do it for us. So we take our data, we randomly pick rows to make like 100 new data sets, and since we picked the rows randomly, these data sets are all different. No two of those 100 data sets are the same. And then we fit a decision tree to each one of the new data sets. And then to make a prediction, we send the new data through all of those decision trees, and then we take the average of the predictions. So instead of making one decision tree that probably overfits, we're going to make 100 decision trees, all of which overfit. But since our data is different and our decision trees are going to be different, we're hoping that they cancel each other out. We're hoping that their errors cancel each other out. Okay? We're going to make a whole bunch of decision trees. They're all going to overfit, but we hope that they balance each other out, and the ensemble of models performs better than any of the individual models. Now that's a very common idea, okay? Making an ensemble of models. Fitting a bunch of models and using the average of their predictions. Our first ensemble model, it is a bagging model. It's called a random forest. And it pretty much works as I described a minute ago. You use bootstrapping to create a whole bunch of data sets, and then you fit a decision tree on each one, and then you use the average of the predictions. A whole bunch of decision trees makes a random forest. See? Now the scikit-learn implementation uses a few more tricks, and it's a lot smarter and better than the very basic random forest that I just described, but it's very easy to use. Okay? By default, it's going to generate 100 new data sets and 100 decision trees. But you can tell it to make more or fewer trees. So to use it, you do from sklearn.ensemble, import random forest classifier, because this is a classification problem. All right, we only have 2 sets. Again, we're splitting the data into train and test sets. It's important that you do that every time, and you fit the model on the training set. Then as you can see here, the decision boundary, even though each one of those decision trees can only draw lines that are parallel to the axes, when you put 100 of them together, you can get something that looks remarkably like a circle. Isn't that fantastic? Now next, this is the same general idea, but I fit it on 3 dimensions instead of 2. 2 dimensions so we can look at it, 3 dimensions so we can get an idea of how flexible the model actually is. And look, it's still really overfitting the data. And the reason it's overfitting so much is because this data was designed to work perfectly with the random forest. Now, here we're just looking at some examples of trees. So I said it made 100 trees. 100 trees. So this is what one of those trees looks like. And this is what one looks like. And this is what one looks like. And this is what one looks like. And you can see that they're all very different from one another, at least these 9. And that's what you want. The more different your trees are, the more they cancel each other out. So what you really want is 100 trees that look nothing like one another. When you have trees that are not similar, their predictions do not correlate, then they will cancel each other out. And that's pretty much exactly the idea behind bagging. The other form of ensemble that we're going to talk about is called boosting. And it is a little more complicated than bagging, but there is a lot of similarity. I mean, they're both ensemble models. So in bagging, we made a whole bunch of new data sets, and we fit a whole bunch of models that will hopefully balance each other out. But in boosting, the idea is to make a whole bunch of models that, like, on their own, each one of them isn't very good. But they do some things well, and then you put them all together, and so each one of them kind of handles their own strengths, and then they form a single good model. So what we're going to do is fit a decision tree on the data, and we're going to see which rows it gets right and which rows it gets wrong. And then we're going to adjust the weights of each row so that the next tree focuses more on the ones that the last tree got wrong. And we're going to repeat that process over and over. And the model is going to focus more and more on the harder rows to predict. And eventually, we're going to end up with like 100 models that are weighted, so they're not all equally important. And then we're going to take the weighted average of their predictions. There are a bunch of packages in Python that specialize in boosting models. A few common ones are LightGBM, which is made by Microsoft. There's CatBoost, which is developed by a Russian tech company called Yandex. And there's XGBoost, which was created by a guy named Tianqi Qin, who is now an assistant professor at Carnegie Mellon University, but I'm not sure if he was already a professor there whenever he invented XGBoost. All three of those actually do boosting and bagging at the same time, and they're all very flexible, and they're very powerful, and they're very easy to use. But they do work differently, and they all have different intentions, and sometimes one of them works better than the others. In general, my advice is to try them all and just see which one does the best. Now, scikit-learn also has a gradient boosting classifier, and that's the one that we're going to use in this example. So, from sklearn.ensemble, import gradient boosting classifier. We've got our fake data again, and we're splitting it into a training and test set and fitting the gradient boosting classifier on the training set. And look at this decision boundary. It's formed some interesting kind of relationships here where it's a little less sure about these points than about these points, which I think is very interesting. But the general idea behind this is that you can see that over time it draws something that looks more and more like a circle. Same thing again, but with 3 dimensions this time. And you can see that it predicts almost perfectly, a little less perfectly than the others, especially on group number 2. But again, that's because the data is really designed to be easy for these models to split up. Gradient boosting models, like LightGBM, CatBoost, or even this gradient boosting classifier, there was a time, not too long ago, whenever almost every Kaggle competition was being won by people using this kind of model. They're very, very powerful, but they do have a tendency to overfit because they are so flexible, and so it's really important to use some kind of regularization, which is what we're going to be talking about next week. All right, the last supervised machine learning algorithm that we're going to talk about today is called k-nearest neighbors. Now, we talked about this a couple of weeks ago when we used the KNN imputer, but we're going to go a little more in depth here. So this algorithm is not similar to the others. I mean, the others have all tried to learn relationships between features and the target, and k-nearest neighbors doesn't actually learn anything. Okay, all KNN really does is find the k observations that are most similar to the one you're trying to predict, and then take the average of those. And the main benefit of KNN is that it makes no assumptions about the data. I mean, it doesn't care what the relationships are. KNN just doesn't care. All right, it looks for similarity, or more technically, closeness. The algorithm calculates the distance between the point you're trying to predict and every point in the training data. It finds the closest ones, and then it takes an average, and that's it. It's very simple, and it's often very effective. So from sklearn.neighbors, you can import the k-neighbors classifier. We've got our fake data, split it into training and test set, fit the k-neighbors classifier on the training set. And look at this decision boundary. That looks pretty good. That looks probably second most like a circle after the support vector classifier. But the support vector classifier literally draws circles. So you expected that to look like a circle. This one doesn't make any determinations about what kind of shape it's doing. It just tries to fit in with the data, and it comes out looking very circular here. Same thing again, but with 3-dimensional data, split it into training and test sets, and then we're fitting a k-neighbors classifier to the training set. And as you can see here, it does really well. Again, this data is kind of designed to be split up easily, but because k-neighbors doesn't find those relationships, it doesn't fit quite as perfectly as all of the machine learning algorithms that do find those relationships. And that's it for supervised learning. There it is. That was supervised machine learning algorithms, and this is really just a taste, okay? There are a ton of algorithms out there, and I just recommend that you Google them. Go the scikit-learn package that we use all the time in here. It just has a ton of stuff in it. Go in there, Google it, read through the documentation, find out what exists. Now, the next video is on unsupervised learning. I think unsupervised learning is super cool. There should be a pop-up here oh no, down here, in just a moment to take you to that next video. Now, if you have any questions, I want you to submit them in the comments below. And I want you guys to go through the comments and read them and answer each other's questions. You don't have to have all of the answers in order to help other people learn. And that's what this is all about. Now, if you did learn from this video, go ahead and give me a thumbs up. And if you want to keep learning with me, subscribe. See you guys in a minute.